Dear colleagues, greetings to everyone. My name is DmitriRachkovskij, and most of my life I conduct research at one of the institutes of National Academies of Sciences of Ukraine. Now I work at Luleå University of Technology. The title of my talk is Hierarchies and Hypervectors, and the plan is on the slide. Consider an intelligent system. The agent.
That's fine. I will just remove this thing so that it's. Yeah.
The agent functioning in some environment. Many researchers believe that intelligent behavior requires construction and usage of the world model. By the world model, we mean a system of knowledge about the external world and about the agent itself. World models of intelligent agents should contain the information about various objects, episodes, and situations, a reaction of the agents to those situations and their outcomes, and other information of this kind. For example, if an agent sees a dog biting a man, the model of similar event should be activated. And then a model may be activated of what could happen before and what to expect next. Then, depending on the goals of the agent, some model of behavior in this specific situation should be activated. We think that the agent has internal models for everything the agent knows about. The models are represented in some way, and the representations are stored in memory. When the agent perceives a sensorial input, it extracts some attributes, such as black, furry, barking, has full legs. It means that representations of internal models of those attributes are activated. There also exist models of objects and relations, or models of events, situations, or episodes, models of action plans, and so on. How can such individual models be organized in the world model? Models should be somehow connected or associated with each other. Many researchers believe that organization of models and of their associations is hierarchical. Hierarchical means arranged in order of some rank. Two main types of hierarchy are as follows. One is part-whole or compositional hierarchy, and the other main type of hierarchy is generalization specialization hierarchy. Other names are categorization, classification, either. These two types of hierarchies are widely used in object-oriented design and in ontologies. Let us consider a part-whole hierarchy. We perceive objects as having parts. For example, a car has parts: engine, body, wheels. However, a car wheel has its own parts: tire, rim, cap. And we may think that those objects, car, wheel, tire, have internal models. And the model of the object whole consists of specific parts, or an object part belongs to some object wholes. And here we see the hierarchy, that is, a part of some whole may have its own parts. Another example of part-whole hierarchy are events of some episode. We may consider events as consisting of their parts, and these parts are the object participating in the events, and some interactions or relations between those objects. For example, the model of the event dog approached ball may include the following parts as models of objects, here dog, a ball, and model of relation approached. The model of the episode dog approached ball, dog beat ball, ball exploded includes models of those three events as its parts. Part-whole hierarchy is immanent to many real and abstract objects. For example, in written language, the atomic parts are letters form words form sentences form text. And if we know some object part, we should be able to access the models of object wholes that have this part. And if we know the model of object whole, we should be able to access the models of its object's parts. So part-whole hierarchy is one basic principle of model organization. Now let us consider the second type of hierarchy, and this is generalization hierarchy, also known as taxonomy, categorization, either. We consider this type of hierarchy to be based on the common attributes of objects. For example, dogs are animals and so share some common attributes with other animals. Dogs have attributes specific to dogs, and individual dogs have attributes specific to those particular dogs. We assume that there exist models of categories. Those models consist of the models of attributes that are common to the objects of those categories. Categories are useful because they allow us to transfer knowledge about the categories to the objects that are instances of those categories. And this property is called inheritance. Some of the categories are more general and some are more specific. Thus, they can belong to different levels of generalization hierarchies. And various subsets of common and specific attributes of object may form different categories. And so an object may belong to multiple hierarchies of generalization type. Since an object may belong to different categories, categorization should be context dependent. For example, it should depend on current situation and the goals of the agent. So we have to implement the model of the world that is useful for the agent. And the model should respect the two types of hierarchy just discussed. When implementing internal models, it is very important how the data are represented. The data representation format determines what can be done with the model, how useful it could be, and its efficiency in applications. Here we are interested in representations used in hyperdimensional computing, the term coined by Pentti, also known as vector symbolic architectures, the term coined by Ross-Geller. Early research have been conducted at the end of 1980s under other names. Representations in HDC VSA are vectors of high dimensionality, that is with many components, such as thousands or millions of components. And with those vectors, we have to represent any model, such as attributes, objects' parts, objects' wholes, events, emotions, and so on. In HDC VSA, various specific frameworks have been proposed. The frameworks are different from each other by the format of vectors they use. In different frameworks, the vector components could be, for example, real numbers or complex numbers or binary numbers. In HDC VSA, two main types of operations on the vector representations of the models are distinguished. These are superposition operation and binding operation. Different HDC VSA frameworks often have different implementations of these operations, and commonly these operations do not change the dimensionality of vectors. To distinguish the high-dimensional vectors employed in HDC-VSA with the respective superposition and binding operations defined of them. Pentic and Nera proposed to call them hypervectors. And so in HDC-VSA, we construct representations of models with hypervectors. Initially, the models are represented using the usual data types of computer science, such as symbols, numerical values, scalars, vectors, tuples of scalars, tensors, sequences, graph. To represent the data of all these basic types by hypervectors, various methods have been proposed. And to be useful, hypervectors are constructed so that similar data produce similar hypervectors and dissimilar data produce dissimilar hypervectors. And similarity of hypervectors is often measured by the dot product or by normalized dot product that is cosine of the angle between the hypervectors. Superposition is an operation of accumulation of several input vectors. Under superposition, the resulting vector is influenced by each input vector independently of the others. We may say that a contribution of a vector to the resulting vector does not depend on the other vectors involved in superposition. Example of superposition operations are component-wise addition of real valued vectors or component-wise disjunction logical OR for binary vectors. Binding is the operation where the input vectors are associated or bound into the output vector by modification of each other. Here, the contribution of each input vector to the resulting vector depends on the other input vectors. Example of the binding operations are component-wise multiplication or circular convolution. There exist versions of binding where we can see that, yeah. Lower.
Okay. Click on those three dots. There is a way to, there's a choice to get rid of that bar. Yeah, try again, click it again. Hide floating meeting controls.
Yeah, this one.
Yeah, next one down.
No.
The bottom one.
What-
Next one,
and then
next down one.
Yeah.
That's it.
Oh, thank you, at last. And so here we see that there exist versions of binding where single input vector is modified to be associated with some state, but the state is represented not by vector. If the state A is represented as a matrix A capital bold, the bound vector B is just obtained as multiplication of the matrix A by the input vector X. For example, A can be a matrix that implements multiplication, implements permutation, and so the result is the input vector with permuted components. Now let us sketch how a rich hierarchical model of the world could be created with hypervectors. Great, but doesn't move. To the next slide.
Click on it.
Maybe click. Oh, now it works. Stochastic. And so, okay.
No.
There we go.
Now let us sketch how a rich hierarchical model of the world could be created with hypervectors, and we'll consider the architecture of associative projective neural networks. This architecture consists of many modules connected with each other. The modules are denoted by ovals. And each model stores and processes many models represented by hypervectors. The models inside a module belong to a certain level of part-whole hierarchy. So the modules at the lower levels deal with some models parts, and the models in higher levels deal with model wholes of those parts. Let us consider a single module. Inside we see several so-called neural fields. The fields keep and process hypervectors. Fields are connected by the so-called projective connections, denoted by arrows in the figure. These connections are one-to-one. They just copy hypervector between the fields. There are two types of fields. The first type is buffer fields, denoted by buff. And this is just working memory for hypervectors. They can also make operations of hypervectors such as binding and superposition. How many buffer fields are inside the module? Wow. And how the connections are organized depends on the particular task. The second type of field is associative field. This field implements the function of long-term auto-associative memory. That is, associative memory memorizes and stores a set of hypervectors, and given some hypervector at the input, the query, associative memory returns the previously memorized hypervector that is most similar to the input. Now, let us consider how construction and processing of models with hierarchical part-whole structure can be implemented in associative projective neural networks. Here, I will simplify the actual processing just to convey the basic ideas. So let us consider just two levels of part-whole hierarchy and with two modules at the lower level. First, let us consider construction of a model whole from its model parts. The hypervectors of models parts are in the modules of the lower level. The hypervectors of the particular set of parts that make up the whole are copied to the higher level module. These hypervectors are superimposed, and the resulting hypervector is stored in the associative memory of the module. In the same manner, other objects wholes are represented and stored in this module. Now let us consider finding the paths by the whole. Note that we formed the hypervectors of whole by superposition of hypervectors of their paths. And superposition operation produces the output hypervector that is similar to the input hypervectors. And so the hypervector of model whole is similar to the hypervectors of its model's parts. So let us copy the hypervector of the whole to the modules of the lower levels of hierarchy, where the hypervectors of parts are stored in their associative memories. We use this hypervector of wholes as a query to these associative memories, and since this whole hypervector is similar to the hypervectors of parts, the associative memories will return the hypervectors of parts. Now let us consider finding wholes by their part. So we copy the hypervector of the part to the modules of higher levels, and their associative memories retrieve the hypervectors of wholes that have this part. And then we can find other objects' parts that form the whole. By doing so, we actually find the association between the paths using the whole as a proxy. These processes can be applied to hypervectors in various modules and various modalities available in the agent, such as vision, hearing, motoric, behavior, etc. For example, let the model's paths be attributes, then the model whole will be object described by those attributes. And if one path is situation and the other is reaction, then the whole will be the association of situation and reaction. Let the path be the name of the object. So by hypervector of the name, we can get the hypervector of the object, and then we can discover the structure of this object whole in lower level modules. So here we see how various types of associations are made by exploiting similarity of hypervectors. It is rather different from association by links or by pointers as in local and symbolic representations. This associative projective neural network architecture may look similar to deep neural network architectures, but actually it is very different. The basic ideas were proposed in the middle of 1980s by Ernst Kussel. I was his PhD student. The hypervectors we used were sparse binary distributed representations. In 1985-87, some designs of parallel hardware for an efficient implementation of APNNs were proposed and tested, so-called neurocomputers. Since 1987, we have chosen the design that can be described as a RISC computer with a long machine word. We started with prototypes with the length of machine word equal to 128 or 256 bits. Then we made larger prototypes with the Japanese company Wacom. 500 bits machine word in 1991 and 2000 bits in 1992-93. The memory size was approximately 100 times more than in the most advanced personal computers at that time. Now we will consider some developments made with this HDC VSA framework. Let us start with analogical reasoning. I got aware about analogical reasoning at the end of 90s from the papers of Tony Plate and later from our personal correspondence. His work on analogical reasoning used his HDC VSA framework known as holographic reduced representations, HRRs. From the analogical side, it was based on the theory of Deidre Gentner and her scientific school, as well as on the research of other cognitive scientists, such as Keith Holyoake, Paul Sager, and their co-authors. Some other aspects of analogical reasoning within HDC VSA were studied by Ross Gaylor and by Pentti Cañero. Analogical reasoning is one of the most interesting and complex forms of reasoning in humans. It is used everywhere, from common sense reasoning to scientific discoveries, and famous example is the analogy proposed by Rutherford between the atom and the solar system. Analogical reasoning requires the ability to operate with complex systems of relations, such as the ability to perceive similarity of hierarchical systems of relation from different domains. In analogical reasoning, the following basic processes are modeled. Representations of known analogical episodes, called the base episodes, are stored in memory. And The elements of those analogical episodes are relations and objects organized in part-whole hierarchy. Then given a new analogical episode called the target or query, analogical retrieval is finding in memory one or more several most similar episodes. Given two analogical episodes based on target, analogical mapping is finding the correspondences between their elements. Then analogical inference. After mapping, it might happen then the base episode has some relations with no corresponding relations in the target episode. But we can conjecture that they're actually present but not observed. These are the candidate inferences about the target projected from the base. Because inference is in analogy is deductive and not inductive. Oh, sorry. It is inductive and not deductive. So inductiveness requires that it should be the candidate inference and conjectures should be evaluated and checked because they need not to be true, as would be if it was deductive inference. So cognitive psychologists discovered a number of properties of analogical reasoning in humans. Some properties are given in this table. And so when some model of analogical reasoning is being proposed, it should demonstrate these properties. Now about analogical retrieval. It is known that humans retrieve analogical episodes with certain similarity types more easily, like shown in this table. For example, humans consider the episode Spot beat Jane causing Jane to flee from Spot to be more similar to the episode Fido beat John causing John to flee from Fido than to the episode Mort fled from Felix causing Felix to bite Mort, especially if we know that Jane and John are humans, Sport and Fido are dogs, Mort is a mouse, and Felix is a dog, is a cat. Tony Plate proposed how to represent analogical episodes with hypervectors and the framework of his holographic reduced representation. Then he used similarity values of those hypervectors as the indicator of the easiness of analogical retrieval. And he obtained results consistent with the results of humans. We designed the representations of the episodes using the HDC VSA framework of sparse binary distributed representations. We experimented with a larger base of analogical episodes that was used to test the best model of analogical retrieval. This is a symbolic model by Ken Forbes and his co-authors known as MAGFAC. We obtained better results than MAGFAC in terms of recall and precision, that is standard quality measures for evaluation of similarity search tasks. Now consider analogical mapping and inference. When we model analogical retrieval by hypervector, we just estimate the similarity of analogical episodes using the similarity value of the hypervectors forms that were formed for the whole episodes. In contrast, non-hypervector models, they calculate the similarity value taking into account the mapping between the elements of two analogical episodes. That is, each element in one episode corresponds to which element of the other episode. Mapping is rather computational expensive procedure, and hypervector approach doesn't need mapping for analogical retrieval, but mapping is required for understanding analogies and for analogical inference. When we construct the representation of the representation, that is the hypervector of the whole analogical episode, we form the hypervector of all its elements from hypervectors of their parts. So those parts may be considered as from lower levels of the part whole hierarchy. Since we have hypervectors of all the elements, it is tempting to map the elements just by similarity of the hypervectors. That is, to put into correspondence the elements with the most similar hypervectors. However, this doesn't work if we use the hypervectors formed for retrieval, because mapping requires information not only about the elements themselves, but also about which elements of the higher levels of part-whole hierarchy the element belongs to. So to fix this problem, we made a new representation of the elements. For this re-representation, we formed the hypervectors of the elements not only from their parts, but also from their wholes. Now the hypervector of the element X is a superposition of two hypervectors. The first one was formed for the analogical retrieval task from its parts. It is denoted as lower here. And the second hypervector contains the roles of the element X in higher level relations to which X belongs. It is denoted as higher here. Using such representations, we obtained correct mappings and inferences for all the analogical episodes that are used for testing the most advanced models of analogical mapping and inference, such as the symbolic structure mapping engine. Now I will turn to more recent work. One interesting topic is equivariance of representations. We start from some input representation of an object. We have a method to transform it to its internal representation. For HDC, we say this internal representation is the hypervector, and then the object is modified. And so its input representation is changed, and to get the hypervector of the modified object, we need to transform its new input representation to the new hypervector. So the question is, can we avoid direct transformation of the input to its hypervector? That is, if we know how the input was modified, can we obtain its new hypervector by the appropriate modification of the previous hypervector? If direct transformation of the input to new hypervector gives us the same hypervector as modification of previous hypervector, then representations are considered equivariant with respect to the modification. Example, let us consider sequences, in the simplest case, sequences of symbols, such as symbol A at 0 position, B at position 1, and C at position 2. Each symbol is represented by its hypervector. denoted in bold here, and to represent a symbol and at its position, we use the repetition of the same random permutation. So, and then the sequence, the hypervector of the whole sequence is obtained by superposition of the appropriately permuted hypervectors of the symbols. And now let us shift the initial sequence from position 0 to position 2. And so the hypervector of the shifted sequence is as follows. However, we can use the hypervector of sequence at 0 position and just do its permutation to the second position. As we see, here we obtained the same hypervectors, A2, B3, C4. And so in this example, the sequence representation based on repeated permutation of hypervectors of symbols is equivariant with respect to the sequence shift. Why is equivariance property interesting? Let us mention two reasons. First, the input transformation of an object to its hypervector is often computationally expensive. The internal modification is often less expensive, as we have seen in the previous example, and so we save resources, at least time. And second, the equivariance property can be the mechanism for the so-called mental transformations. As proposed by Shepard, some experiments with humans seems to indicate that the brain makes internal transformations of internal visual models of objects. But let us continue as follows. If we shift the sequence, the hypervector representation will become dissimilar because random permutation destroys similarity of hypervectors. For example, hypervectors of these three sequences are not similar, though sequences look very similar to us. Or consider some spell checking examples. Small changes in letter positions still produce recognizable words. However, the hypervector representations will have low similarity values. To preserve similarity of symbols with themselves at nearby positions, a number of hypervector methods have been proposed. However, those methods are not equivariant with respect to shifts. One solution that preserves both the local similarity and the equivariance properties is as follows. Let us consider an example. We want the hypervectors of a symbol to be similar at nearby positions as shown in these graphs. For example, these are similarities for the setup we call similarity radius R equal to 3. So we do the following. We generate the atomic random hypervector for the symbol A, and then we form the hypervectors at various positions using permutations and superpositions as shown in this slide. It can be easily checked that this hypervector representation gives us the required similarity properties and is equivariant with respect to the sequence shift. This permutation-based solution can be used in many HDC-VSA models, and instead of permutation, this approach can also be used for the HDCVSA frameworks that allow recursive binding, such as frequency HRRs of Tony plate. The equivariance property allows an efficient calculation of similarity measures that checks similarity at different positions and selects the maximum value. This approach can be extended to two-dimensional spatial objects such as images. Let us consider its application for visual place recognition. The task is to compare images from one data set to the images from another data set and to find the images of the same place. Example of the same places are shown in this figure. In the setup investigated by Pierre Newberg and his co-author, images are initially represented by the DELF features at their two-dimensional positions. DELF stands for deep local features that are 1000 dimensional real valued vectors extracted from image at various positions. Using HDCVSA approach, Pierre Newberg and co-authors transformed the initial image representations to the hypervectors and then just compared hypervectors. They improved state-of-the-art results. In our current joint work with Pierre Newberg, we transformed the DELF image descriptions to hypervectors using the permutation-based encoding approach that I have just described, extended to the two-dimensional case. We got some improvement of results, and the major difficulty of this task, as I see it, is that different data sets naturally require different parameters of hypervectors. But the considered setup required the same parameters for all 23 data sets. We also investigated many different modifications, including changing real valued hypervectors to binary ternary, using sparse representations, methods for increasing dimensionality of hypervectors, and we hope to include it in future manuscript, these and other options that we have proposed and tested. They may be interesting for other HDCVSA frameworks and applications. And now, some topics for future research. The representations I considered during the talk were instances of part-whole hierarchy, such as rather deep hierarchies in analogical reasoning, rather shallow hierarchies in spatial objects such as sequences or images. And so what about the generalization hierarchy introduced at the beginning but avoided so far? Where this hierarchy is formed and how? This problem is rather unexplored. And we think that such a hierarchy could be formed in the process of unsupervised learning in matrix type distributed auto-associative memory known as Hopfield network. Hypervectors we consider here are sparse binary distributed representations, that is a small fraction of one-valued components. They have a small fraction of one-valued components, and the rest of the components are zero. The hypervectors of objects are formed as superpositions of hypervectors of the attributes. So when objects have similar attributes, their hypervectors have many common one components. That is, they are correlated. And what happens when we memorize such correlated hypervectors in the Hopfield network using the Hebbian learning rule? The combinations of one components that are often met together in the memorized hypervectors will get larger connection weights And in the process of retrieval, the neurons with larger connection weights get larger input activations and so become active after thresholding. The neurons connected together were called assemblies by Donald Hebb. He also called the neurons often activated together and connected with high weights as cores of assemblies. And neurons with low connectivity, he called fringes, that is some periphery. So in our associative field, in the process of learning, the assemblies emerge with their complex and rich internal structure that has cores and fringes. Cores correspond to combination of attributes often mapped together. These are models of categories. Fringes correspond to combinations of attributes seldom met together. These are models of category instances. So in the process of Hebbian learning, generalization hierarchies could naturally form in the structure of weight connections inside the assemblies. By changing threshold values, we can control if only a strong core is activated or less strong core of fringes as well. And these are rather unexplored, as I mentioned before. The distributed associative memory with assemblies can also help context-dependent and goal-dependent categorization. The attributes may be not only perceptual, but also the models of the agent's goals. So assemblies will include hypervectors of goals. Then common subsets of attributes of various objects will cluster in the cores corresponding to certain goals or contexts. The same perceived attributes of particular object will contribute to multiple cores of assemblies. Each core will include the subset of object attributes that occur with the corresponding goal. As a result, depending on the current agent's goal, the same object as the input will activate different cores, that is, different categories. Also, representation of a goal may activate assemblies of various objects that can help the agent to achieve the goal. As for other topics for future research, I will just read them from the slide. So, development of HGC-VSA for analogical mapping with parallel constraint satisfaction in distributed auto-associative memory of matrix type. Auto-distribution detection, brain-like representation and processing of sequences, temporal context, hierarchy, and segmentation. Vision, equivariance and various beyond just shift. Transformers, shallow and wide based on associative memories. Knowledge and reasoning, including common sense. There is a number of data sets for the latter task, such as mentioned on the slide. And that's all for now. Thank you.
Thank you, Dmitri, very much for your talk. So now we have some time for questions again, and we continue the discussions afterwards.
Well, first of all, great talk. Thank you so much. I'm really curious to get your thoughts on like actually building these systems. At some point, moving up the hierarchy, like obviously in our brain, we just have such a massive amount, like on the order of 100 billion neurons. But with these smaller vectors, how would you envision like building such a system that has all of these component models in it, like the hierarchical models? Would you have like kind of one central representation that's passed around, or would they all kind of have their internal representations and communicate with each other separately? I don't know if that question makes sense. Like, I guess my question is, would you change the dimensionality of the vector or use multiple different vectors?
But if you look at this architecture, it actually preserves the dimensionality of hypervectors. But you see, there are obvious ways to change it at its stage. So both options are possible, but I of course don't know which should be used at the moment, which is better. I'm not sure. And in general, yes, we have even so long ago, we wanted it the architecture to make such an architecture that could be scaled to the brain size and even produced those efficient neurocomputers for its implementation. Yes, but it was not implemented because we need some data at the input, some structured data that shows which is the part, which are the holes to make it those hypervectors. But so we need those structured data, and we have them just, for example, in knowledge bases and in logical reasoning, but not for other problems. And so the question is, and what to do if we can't get those data? But the principles of vector representations of different types of computer science can be used more locally, such as, for example, taking graphs, convert them to hypervector and classify. So a lot of our work was dedicated to those some more reachable things and more simple things. Thank you.
Thank you for the talk. So I was wondering if you could say a bit more about your motivations for using like the sparse binary distributed representations in particular. Like, is it for I guess, relative to, say, holographic reduced representation,
yes,
or +1 -1?
Yes. I'll answer in brief. Okay. First, when we started our work, we did not know anything about holographic reduced representation because a little bit at the same time. Okay. But from the very beginning, the motivation was to make implementable model. And so inside each of the modules, we need associative memory. A dense associative memory of Hopfield type, we thought it. And its capacity in terms of number of stored vectors very low for dense representation, for usual Hopfield network. And for sparse vectors, binary vectors, it is huge. It may be more than the number of neurons. That's the dimensionality of the vector. And so this was one of the motivations. And then if you operate with those sparse binary vectors, you can make very efficient hardware for implementing it. That's all for now. Let's discuss later.
For sure. Thank you.
Dennis.
It's not a technical question, but I'm curious about the photon meter. Not everyone recognizes it. That's the photon actually meter, right? Sitting in front of that your computer. Was it like a random photo, or was it done on purpose? Like, was it all like set up just to take that photo? What is the story behind it?
It was made randomly, but now it appears not random. Yeah, quality is bad, but here is a calendar, and the number here is 1989. So it shows when we made that neurocomputer. And if you look at the screen, it will show multi-level hierarchical network of this type, but simpler one for sequences processing with those part-whole hierarchies.
So we were like doing nothing for the last 50 years, right?
Exactly. Absolutely, yeah. Just put some things, some small bites of things from those ideas and try to implement and publish.
I have a question of my own. So we have quite some people here working with hardware and the unconventional computing and stuff. So do you think your experiences with this neurocomputer you did back then would be useful in some context for current development?
As I told you, our design was based on the implementation of those Hopfield-like associative memories, and it is practically unexplored since then time, and certainly it doesn't used by others now. Though the recent works of modern Hopfield networks speak about Hopfield network, but it is a very different design because it is not distributed memory, not okay, and another issue was that for efficiency we even did not use the Hebbian learning rule. Because it produces not non-binary values at the output. So Wilshire type rule produces binary values, but it is not suitable for. So it is not suitable for forming cores and fringes, because there are no gradual connections with more strengths or less strength, because they are all in Wilshire memories, they are all 1 or 0. But we have some means to implement those gradual connections inside the field. But anyway, those designs I spoke about were for binary vectors, not only as hypervectors, but also binary associative memory. So this is very specific. But if we avoid those binary memories, but just consider it as making matrix vector multiplication, it will be useful for in such a context.
Thank you. Any more questions? Or we are.
Ross.
Yeah, please.
Thank you, Dmitry. My question is, I think, a continuation of Kylie's. I'm interested in implementation. On your slide 17, perhaps, if I've understood what you're doing correctly, you've got these modules, and it appears that you're assuming that the modules are implemented with separate pieces of hardware, and so there's essentially a design choice. That you have an external programmer who's designing the system and says, I will have these modules, I will connect these modules in this pattern, and it's implied that there's also a finite number of levels in the hierarchy which are fixed in advance. So do you think so? Obviously that's a design effort and requires the designer to be able to properly analyze the problem. Is there a potential for these systems to self-learn their organization in some sense, so that given some appropriate initial design, you could expose it to a class of problems and let it modify itself in some way?
Yeah, thank you. But regretfully, it is unexplored. So as I told before, we even did not explore those learning inside the associative memory, and even less how the structure could be evolved other than by evolution. So at the moment, I would not say much more.
Thank you.
Regretfully, of course, for such a thing.
Thanks. So it's related to this point. The closest comparison would be knowledge-based systems and expert systems from a the whole part generalization hierarchy perspective, especially from that timeline. Is that a fair argument?
About generalization hierarchy. But actually, the simplest thing is take artificial examples to test it. But if you go to real world applications, we are open. We did not consider that setups as being more or less appropriate. So we should analyze it.
Yeah, there's potential there too.
Yeah.
All right. So if there are no more questions at this moment, so please collect them for our outside sessions. So we thank Dmitry once again. Thank you.